Good morning, folks. We are into third part of lab number 5. In first part, I covered the theory of the eutectoid reaction in steels. Then in the second part, you saw that we prepared the specimens. Now in this third part, we are going to do the microstructural analysis. So here are our specific objectives. We are going to identify the microconstituents and their compositions in each micrograph. We are going to calculate the expected amount of perlite in each micrograph and compare it to the calculated amount. We are going to process each image and determine the amount of perlite. And then we are going to look at Knoop indents made into each of these specimens and measure the length and area of these Knoop indents and compare the Knoop and Meyer hardness numbers. And we are also going to look at a rule of mixtures to determine the Knoop hardness of each microconstituents. And as usual, you're going to critically evaluate the numerical results, make summary conclusions, and submit a lab report in the specified format. Okay, so we have two sets of specimens. I have demo specimens, these three in the second column, and then we have your assignment specimens. The assignment specimens were the ones you saw being prepared in part 2 of the lab. We didn't show you preparations for my demo specimens, but basically the preparation was identical. So I have a demo Excel template. So if you want to follow along with my demo, please prepare this template. The PDF is posted on my courses, and your actual assignment sheet would be very slightly different. So you would be able to make easy changes if you want to prepare this demo Excel template. I also want you to create a word table. So let us go and create this word table. So I'm going to fire up Word, blank document, and insert a table. And let's see, we have 3 samples. So each image, and I want about 6 rows. So one image and a caption. Okay. So I have a 1008 annealed steel microstructure. So let me open this image. So this is image of a 1008 steel sample, a fully annealed, and it has got this scale. Now when we analyze images, I don't want to have the scale here. So what I'm going to do is I am going to crop the scale out. So I'm going to draw a rectangle and I'm going to just miss the scale. Go to image, crop. So this is the image I'm going to work with. This is my original image. So I'm going to copy it to the system, go to the Word document and paste it. Now I want all my images to be 3 inches in width. So I'm going to change the size and position to 3 inches so that it'll fit nicely. So this is my 1008 steel cropped image. And the percent per light calculated, therefore, in this would be, and let's do this calculation. So we start with austenite at high temperature. We slowly cool it. We get perlite and we get pro-eutectoid ferrite. Now the composition of the alloy is 0.08%, 1008. Perlite is 0.76%, and alpha P is 0.022% carbon. We begin with 100% of gamma. Let's say we have WP amount of perlite and we have W alpha P amount of pro-eutectoid ferrite, which would be 100 minus WP. So doing our carbon balance, we will get 100 times 0.08% is WP times 0.76 plus 100 minus WP times 0.022. So now if you want to, we have one equation, one unknown, we want to get WP out of it. So WP out of it is going to be 0.08 minus 0.022 divided by 0.76 minus 0.022 times 100. So this is our C alloy. So when we calculate this, we will get let's get a calculator. we will get 7.9%. So our W alpha P would be 100 minus 7.9%, and that would give us 92.1%. So now if we fire up our Excel spreadsheet, so of course we have our title, method inputs. You might want to look up the model numbers of these hardware. This is our three samples, 1008, 1023, W1, and we have our parameters. So I took the image at 500x. So let's see what our resolution is. 1 divided by this. So our resolution, let's round it up, is zero point 0.2 microns per pixel. So for Knoop hardness, this is our kappa, and this is our force. And we just calculated that for 1008% per light is 7.9%. And of course, alpha P is 100 minus that. So that is our calculated amount. Okay, so now let's measure this. We are only interested in percent area, and this is all per light. So what we are going to do is we are going to take this image. It's already 8-bit. You can see if it was colored image, we would have converted it to 8-bit. And then we are going to adjust the threshold. And you can see automatically it does a very good job of doing a threshold. So we are going to apply, close this window. So now we have converted this to binary. So we are going to go ahead and process this binary image, and we are going to fill all the holes because this was all per light. And then we are going to go ahead and analyze particles. So of course, all of these small particles are dust particles. They are not per light. So what we are going to do is we are going to search from size, say about 10 pixels square. We are not going to worry about the shape of the particle. We want to display the results. We want to clear any results that were there. We want to get a summary. And we want to include if there were any holes. So we say OK. And we see that our percent area is like 12.67%. Oops. And it got 66 particles. So that's kind of a lot. 66 particles is a lot. So let's redo this again. So this time we are going to go ahead, analyze particles, and we want to look at the outlines. And this time, let me increase the size instead of 10 to about 100. So it shows me the outline of the particles. Notice that by going through 100, I have taken care of all that small dust particles. So now I have only 27 particles and the percent area is 12.46. So we are going to round it up to 12.5. But this is what I measured. So I am going to copy this image and put it in my Word file. And again, I want size 3-inch, width, so this is 1008 steel processed image and percent perlite measured is 12.5%. So this was 7.9%. So here is something interesting. Calculated was 8% and measured is much larger, even after we ignored all these dots. And this should not be surprising because all we did was calculated is statistical average and we just took one image. It may be just that this image had a lot of perlite, whereas if we took another image, it may not have as much perlite. Okay, let's go ahead and look at the next image. Now, this is a very beautiful image because after etching, it also shows the pro-eutectoid ferrite boundaries. And these dark areas not resolved are all perlite. So this should be the two-phase microstructure. So let's go ahead and copy to the system. Size it to 3 inches. And give it a caption. So this is 1023 steel. We didn't do any cropping, original image. And we can calculate the percent perlite. And we put it in our formula. We have 0.23% carbon minus 0.022 divided by 0.76 minus 0.022, and which gives us 28.2%. Okay, so let's process this image. So we are going to do the same thing. First, convert it to 8-bit. It's already 8-bit. We don't need any cropping. So what we are going to do is threshold. So now you can see in thresholding, it has captured quite a bit, very nicely, the perlite. So we can apply, close, and again we can go through analyze, particles, 100 through infinity. Okay. And again, notice that we have not counted all these dots, etc. So this time our percent area is 13.3. So let's go ahead and say this is 13.3. Oh, calculated was, let's see, go back, 28.2. Pro-eutectoid component, 100 minus 28.2. And let's look at our measurements. So our measurement was 12.5 here, is 13.3 here, so this is our processed image. Percent per light calculated is 13.3. Okay, let's also enter it from previous one. This was 12.5. Okay. Pro-eutectoid component. Pro-eutectoid component. Again, our value is much, much smaller than what we expect, but this is just one of the images. Let's keep track of it. So we are going to take this, copy, to system, paste, size it to 3 inches. Okay, so we are ready for our last image. Now this is a colored image, and again this has a label here, so we are going to crop it. So image crop. So this is the image we are going to work with. So let's copy it to the system. Go into our Word sheet. Size it to 3 inches. Give it a caption. So this is W1 1.3% weight percent carbon steel cropped image, and percent per light calculated. In this case, let me use my calculator, and it'll be 1.3 minus, sorry, 6.7 minus 1.3 divided by 6.7 minus 0.76 times 100. So we will get 90.9%. So let's enter that into our spreadsheet too. 90.9%. So that means our pro-eutectoid component would be only 9.1%. Okay, so let's process our image. So since this is a colored image, the first thing we are going to do is convert it to 8-bit. Then we are going to threshold it. So let's understand what this image is all about. So these white areas surrounding these perlite colonies are pro-eutectoid cementite. So that's what we want to essentially discriminate against, these river-like white, river-like things surrounding each grain. So this time I'm going to adjust so that I can capture much of this perlite. So I'm going to apply, close, and process is a binary image. I'm going to fill all the holes, analyze particles, and again I'm going to ignore 100 through infinity, or ignore anything smaller than 100. Okay, so you can see it did pretty good job. It missed some of it, so it is overestimating the perlite. Let's see what the value is. So it says to us that it is 91.4%. So let's go ahead, copy this to the system. Size 3 inches. and a caption. So we have W1 steel processed image percent perlite measured is, we just got that value, which was 91.4%. So in this case, we got pretty close to what we calculated, but again, it was just a coincidence. Remember, we know that we overestimated amount of perlite here. So I'm going to save this file, save as, and let's just suppose we say trial. So this would be part of when you do on your assignment images, this would be, this word sheet would be part of your report. So let me close all these windows. So you saw we processed all of these 3 images and we got a word table. And we did this microstructural analysis. We are going to see how much is our percent difference. Okay, folks, so we have done the microstructural analysis. So we just calculated that for W1, it was 91.4%. So that means the pro-eutectoid component, cementite, would be 100 minus 91.4. So now we are going to take the percent difference, which would be measured over calculated minus 1 times 100. Of course, this is a very large difference, but let's go ahead and copy this formula only. So we can see that for hypoeutectoid steels, we had large differences. For hypereutectoid steel, we just coincidentally happened to match the result fairly well. Now, this is what is going to happen because we just took one image. We should do statistical analysis. We should have taken many more images and then have averaged it. So for your assignment, I've given you 2 images per sample, one at 200x and one at 500x. And it's up to you whether you want to measure both the images and average them, or you want to just pick whichever one gives you better result. Okay, folks, I just want to let you know that these measurements that I'm showing you on the right hand side may not match my slides because the slides were prepared before I did this recording. So these are my measurements from my first trial. Okay, so the second part is about the Knoop indents. So I made 6 indents on each of the 3 samples. So we want to measure them and get the Knoop hardness of these indents. So let's fire up our Fiji again. We are going to open our first image, 1008. So all the images are taken at 500x. So I'm going to set up my scale. 5.014 pixels is 1 micron, and that's my global scale. Then I'm going to set my measurements. I'm interested in the long diagonal, so I'm interested in Ferret diameter. I'm also interested in this projected area, and I have all this display label, scientific notation, add to overlay, 5 digits. Next, for each image, I'm going to crop the image. So I'm going to capture this indent in a rectangle. I'm going to crop it. Since this is a color image, I'm going to change it to 8-bit gray level. Then I'm going to threshold it. And the computer does a pretty good job of choosing an automatic threshold. So I'm going to apply it, close this window, and then I'm going to analyze particles. So what I want to do here is I don't want small particles. I don't want to measure these particles, and they are definitely less than 100 microns square. I don't care about the shape. If you want, you could choose an outline so you can see what is being measured. I want to display results. I want summary. I want to include holes in a later on. Some of the indents you will find there might be a hole here. So I want that filled in and counted in the area measurement. So once I say OK, it makes the measurement. There's only one particle it found. And here is our summary. Let's go ahead, open the next. Now we're just going to draw a rectangle, crop, change it to gray level, threshold it. So now it is black and white. And now we are going to measure it. So we get another measure. So this way we are going to go 1, 2, 3, 4, 5, 6 for 1008, and then 1023, and then W1, and we will get our summary sheet. So this we are going to save, and we are going to transfer it to Excel. Okay, so I have made all the measurements. They are saved in this summary.csv file. So let me copy it over. So I'm going to open the summary file, copy all these values, into my spreadsheet. Name it. So this is Fiji. And I'm interested in my file name. So I'm going to go ahead and copy, paste it. I'm interested in area. And I am interested in Ferret diameter. Okay, let's adjust some. We have only 5 digits here, so let's adjust this. Now notice we can only measure length up to 0.2 microns, right? That was our resolution. So therefore, at best we can measure it to 1 decimal digit. Okay, so let's close this. Okay, so let's go ahead and process the spreadsheet. So I've got all these things that I'm going to show you. They are all in there. So let's go ahead and type some formulas. So we begin with giving names. So this we are going to call kappa. This we are going to call F, force. So our formula for Knoop hardness is kappa times F divided by the length of the diagonal square. Since it's in micron, we are going to convert it to millimeter square. For Myers hardness, force divided by area. Again, this is in millimeter square. This is in micron square converted to millimeters. Percent difference, we are going to take Knoop hardness divided by Myers hardness minus 1 times 100. Okay, let's adjust some digits. We want 1 digit here, 1 digit here, and 1 digit here. And we are going to take all these three formulas, copy them down. Okay. So let's see how the Knoop hardness compares to Myers hardness. So we are going to insert a plot. Move it to a new sheet. And then we are going to adjust fit trend line, etc. We want a straight line. Display the equation. And you can see we get a pretty good straight line fit, 0.96. So let's go ahead and calculate these. So we are going to say intercept is y values, comma, x values. Next, slope is y, comma, x values. So we expect the slope, if everything was ideal, it should be 1. Intercept should be 0. Let's look at r square. Y, comma, x. So you can see we get a very nice line fit. Okay, let's do some more analysis. Let's calculate the average hardness values. So we want average of the first 6. Average of the next 6. Average of the next 6. Red sample. So the first thing we notice is as percentage carbon increases, the hardness increases, the average hardness. Okay. So there is a very interesting thing we can do. So here is a plot, by the way. I have adjusted the axes, etc. So I'm sure you know how to do that. And let's talk about a concept called rule of mixtures. So let's suppose we have two phases, alpha and beta, and they are in this proportion. And let's suppose they have hardness alpha and beta. So what we can expect is that if we use rule of mixtures and we take the weighted average, this would be the resulting hardness. So we are going to use this idea. So let's suppose we have three phases or microconstituents. So now we can say hardness is therefore W1 times hardness 1 plus W2 times hardness 2 plus W3 times hardness 3. So if we knew the weight fractions and we knew the overall hardness, and we wanted to find the hardness of each of these three microconstituents. So we have perlite, we have proeutectoid ferrite, we have proeutectoid cementite. So if we had three samples whose average hardness we knew, we could set up three equations and three unknowns and solve for the hardness of each of these microconstituents. So you may remember from linear algebra, suppose you have three equations and three unknowns, you can write them as A times X is equal to B. And then X is A inverse times B. So what we can do now here is that we are going to use the calculated values and we are going to name these values as matrix A. So that's our matrix A. And these average hardness values are our matrix B. So we can calculate therefore the hardness of each of these microconstituents, saying matrix multiply inverse of A by B, and since we want multiple cell values, control shift enter. Oh, forgot, since this was in percent, so we need to multiply it by 100. So let's go ahead, multiply by 100. Control shift enter. So if our values were very representative, we would have gotten a very decent answer here. Since we got this negative value, our solution is not very good. But in general, what we should have found was that this cementite should have been extremely hard. Next would be perlite, and softest would be alpha. So we can see, therefore, our these calculated values are not consistent with our hardness values. Okay. Oops. So that was our discussion. Hope you were taking some notes. If you have other observations, I'm very willing to have a discussion with you via email or even have a meeting. Take care.